All right, greetings, 215 class again. It sucks that I have to do it this way, but I don't want to miss out on a day of information. So I'm going to try to get you all the information here via video. Just from the top, I'm going to say that you should probably read through these sections because I'm giving you all the notes because you're not writing anything down. It might be, you might not retain the information as well. I guess you could always take the unfilled notes and fill them in as we go. They say that you learn better as you write them down. It's 10:46 right now on Saturday. I am all decked out in my Sparty gear. Got the big S right there. So as of right now, I'm in a pretty decent mood because the game hasn't happened yet. So it remains to be seen if I'll still be in a good mood after that. So let's just get right into it. I'm going to go through this quicker than I would in class because you have the definitions already written down for you. If this is something that you want to write them down, just hit pause after every time I give a definition. You can write it down, and then I'll go into my little spiel about everything. So we're moving on to Chapter 3. We're starting with one quantitative variable. Chapter 3 is going to go a little bit quicker than Chapter 2 because we've already laid all the groundwork in Chapter 2 for all the different things that we can do. So on that little spiral graph, this spiral is a little bit tighter than the Chapter 2 one. This should go quicker. But that being said, when we were dealing with one categorical variable, we're very limited in the types of output that we can use to summarize. So we had a bar graph, pie chart, frequency table, and relative frequency table. So those are really the only four things that we do for categoric data. We can talk about counts, and we can talk about percentages and stuff like that. Once we get to quantitative data, there's a lot more that we can do. I guess in terms of setting up our descriptive statistics, this might take a little bit longer than Chapter 2, just because dealing with quantitative data is so much more powerful than dealing with categoric data. So let's just get into the definitions. So Section 3.1, descriptive statistics, the 5-number summary, and percentiles. So a percentile, the pth percentile is a value such that p% of all data is at or below that value. My guess is most, if not all of you, at some point in your life have taken the ACT or the SAT. And so you take it and you wait the 4 or 5 weeks and they send you the results back. And they give you a percentile. And let's say that you scored in the 87th percentile. That's pretty good because what that means is you did better or as well as 87% of all people that took it. If you scored in the 13th percentile, my guess is you're not in my class. If any of you have kids or hope to have kids someday, they do what are called well visits for the babies. And some of the things that they do at these well visits is they measure your baby's height, their weight, and their head circumference. So I just wanted to give you another example of a percentile. All three of my kids, all three of the J's, Jordy, Jackson, Jay, they're in like the 30th to 35th percentile in height and weight, and they're in like the 90th percentile for head circumference. So big noggins are hereditary. So what that means is they're taller, they're heavier than 30% of all babies at their given age, but they have a head circumference that's larger than 90% of them. So I apologize to my kids. The next two definitions, my hope is that you know what these are. But the minimum, it's just a big fancy word for the smallest data value. And the maximum is the big fancy word for the largest data value. The median, we're going to talk about this again when we talk about measures of center. But the median is the middle number of a data set when it's ordered from smallest to largest. So if you have an odd number of observations, like 5, then you have a middle person. So that whatever their value is, that's the median. If you have an even number of observations, there is no middle. You'll just take the average of the middle two. So if I wanted to find the median height of our class, I could line you all up from tallest to shortest, and whoever is in the middle whatever your height is, that is the median. Next up, we have our quartiles. So we have the first and the third quartile. We don't talk about the second quartile, at least using that name, because the second quartile is just the median. But the first quartile, shorthand for that is Q1. Think quartile, you think quarter, you think a quarter of the whole, or the coin quarter. 25th percentile. So using the definition for percentile up above, 25% of the data is below. I don't know which way. I won't use hand motions because I don't know which way this is going to show up. So 25% of the data is below this value. 75% of the data is above this value. And then very similar, third quartile, Q3, 75th percentile. 75% of the data is below, and 25% of the data is above. I meant to mention this off the top. Hopefully you guys can understand me. I know that the microphone in my computer is not that good. My voice is nasally, typically, and I'm underneath the weather. So kind of a perfect storm, but hopefully you can get this information without too much trouble. So our 5-number summary. It's a quick snapshot of quantitative data. And what a 5-number summary does is it breaks the data down into 25% chunks. You can see the form right here. This is always the form that we are going to use. If you ever see 5 numbers inside parentheses with commas between them in a statistical setting, almost always that's going to be a 5-number summary. We start with the smallest number, and then we go in ascending order. So, and this is the form that we use. So you're going to open your parentheses. You're going to put your minimum value, and you don't say minimum equals the value. You just put the value, comma Q1, comma median, comma Q3, and then comma maximum. So a quick snapshot. Some of the stuff that we're going to continue to talk about in this video, we can calculate just based off of these 5 numbers. There's a certain graph that we can pretty much make just off these 5 numbers. So it's only 5 numbers. It's really quick. It's really powerful. We can tell a lot of information just from our 5-number summary. I have a thought question down here, and typically when we're in class, I ask the class, and they give me answers. Can't really do that here. But the thought question, what would be true about the 5-number summary if we had symmetric data? If you want to think about this for a minute, go ahead, pause the video, and then I'll give the answer, obviously. But if we have symmetric data, the symmetry, remember, symmetric means both sides are roughly mirror images of each other. So our symmetry is going to lie through our median. Well, if we have symmetry through our median, then the distance from the median to our quartiles is going to be the same. That's a little bit more important, but if it's perfectly symmetric, very few things in life are ever perfect, but if it's perfectly symmetric, then it's also true that the distance from the median to the minimum and maximum are the same distance as well. And then we can use the transitive property to say that the minimum to Q1 is the same as Q3 to the maximum. But very few things in life fit perfectly into the little boxes that we want to put them in. So if the quartiles are roughly the same distance from the median, if the minimum and the maximum are roughly the same distance from the quartiles or from the median, then we'll probably say that the data is symmetric. Okay. When we interpret a graph of quantitative data, we want to focus on the following. So we want to talk about the center of the distribution, the variability, the spread of the distribution, the shape of the distribution, and the presence of outliers in the distribution. So the center, think of the center of the distribution as the point that splits the data in half, so the median. So that about half the data values are less than the center and about half the data values are more than the center. This is a visual representation of where the median falls on the graph. Okay, I did put the word median already in there. For some graphs, it's going to be easy to pick out the median. For other graphs, not so easy. There's going to be other features that we can talk about. But think of center as, the middle point or a typical data value. Yeah, and then depending on the graph that we use, we'll be able to determine different things that would quantify the center of the data. The next thing, variability. To interpret the variability of the graph, ask yourself the following questions. And I'll preface this by saying variability is a little bit harder to talk about than the center or the shape or outliers, because a lot of times variability is going to be, it's easier to talk about in relative nature to something else. It's very hard to just look at a graph and say, oh, this is a number that quantifies the variability. But a couple questions that we can ask, are the data values clustered together? If they're all scrunched up, we're going to have low variability, or are they more widely dispersed? The more spread out they are, the higher the variability. If the data are widely dispersed, are the data values dispersed equally around the center, including large variability, or are most of the data values near the center with just a few extremes indicating less variability, or are more of the values at the extremes with just a few values near the center indicating very large variability? So the more data points that are clustered together, the smaller the variability, even if you have a couple little guys out here on either side. But if we have a bunch of data on the outside with not very much in the middle, that's going to be a lot of variability. The shape. To interpret the shape of the graph, ask yourself the following questions. Is there skew to my graph? So again, one possibility here is symmetric if both sides are mirror images of each other. Then we say that the data is symmetric. It can also be skewed left, or it can be skewed right. So one of these three options. I found a couple graphs here. Hopefully you can see this up at the top. So skewed left, that just means that the data values to the left are more spread out. Skewed right, that means that the data values to the right are more spread out, and the stuff to the left is really scrunched together. Symmetric, if we draw a line right down the middle here, both sides are roughly, well, here they are mirror images of each other, but again, will always be perfect mirror images. Let's go back to the notes. So one thing that you can tell about quantitative data, which direction is it skewed? Another thing with the shape, how many modes are there in the data? Now, typically, in your old statistics classes anyway, when we talk about the mean, which we'll get to, the median, and then the mode usually gets thrown in there as well. And that's it's the most commonly occurring number, the number that shows up the most. We're going to shy away from talking about the mode as a measure of center. One of the questions that I asked you guys was, how many Facebook friends do you have? And now, if you don't have any Facebook friends, I just don't put in an entry. But I used to put in 0. And what happened was 0 was the most commonly occurring number because there were more people that had 0 Facebook friends that just didn't have Facebook friends than had any other individual value. So no one will ever argue that 0 is a good measure of center there because it's on the extreme. It's the smallest number of Facebook friends that you can have. So in statistics, when we talk about a mode, we're no longer talking about just the one data value that is most commonly occurring, but rather the peak where there's just a lot of data. So for Facebook friends, that might be around 500. We'll see that here shortly. But when we talk about a mode, we're talking about a peak where there's just a lot of data, and the further you get away from that data, the fewer observations that there are. So if I go back to this graph, all of these are unimodal. They all have one distinct peak. Here it happens to be on the right-hand side, so this is in the middle, and then this is on the left-hand side. But we can talk about how many peaks there are. So if there's one peak, like those three graphs, we say that it is unimodal. So uni meaning one, modal, talking about modes. There is one mode. It is unimodal. Most things in life are going to be unimodal. Most things that we measure. If we do height, if we do Facebook friends, if we do Facebook photos, shoes, average number of hours of working out, if we measure everyone's hand spans, there's going to be a lot of people that all have very similar hand spans or all have similar Facebook friends, and the further that you get away, the fewer observations there are going to be. Unimodal shows up a ton. Just nature causes that. We may also see some graphs that are bimodal. Not a ton of great examples here, but there is one, and I find this fascinating, and that's Old Faithful Geyser. The duration of the eruption. So Old Faithful, the geyser out in, I think it's Yellowstone National Park. You guys know what a geyser is. So the water sprays up. If you measure the lengths, the amount of time that each eruption lasts, it follows this bimodal pattern. Now, to be clear, it doesn't matter that this peak is a little bit higher than that peak. There are still two distinct peaks here. So it comes up, it goes back down, it comes up, and it goes back down. So there's a lot of eruptions that last right around 2 minutes. There's a lot of eruptions that last right around 4 minutes and 30 seconds. So this is bimodal. There are two distinct peaks here. And then finally is the distribution bell-shaped. So that normal distribution that we talked about in Chapter 2, we're going to hit that a lot harder here in Chapter 3 once we have a good grasp of quantitative data. We can do so much more with these normal distributions than we've already had. And then outliers, these are extreme data values that differ greatly from the rest of the data. If, assuming I was in class, and if all of you guys were there, for pretty much every class, if we talk about the age of everyone in the room, I would be considered an outlier because my value is so much different compared to everyone else's value. Now, if you're a non-traditional student and you're around my age, you're just an outlier with me. All right, so now the first graph that we can talk about when we're dealing with quantitative data is called a box plot. You may have heard this called a box and whiskers plot before, but here's a quick example of it. Oh, it's on the screen perfectly. So here's a box plot for number of shoes. So shoes was one of the variables that I collected data on. Well, what I want to do is I want to approximate the 5-number summary here. I gave you plenty of room over here to write. Make sure that you put it in the correct form, so they're all in parentheses in ascending order. So our minimum is this guy right here. So the end of this whisker, if I follow this over, let's call it 4. If I ever ask you to approximate a 5-number summary, I'll give a little bit of a range. So if you put anything between 0 and 10 there, I probably accept it. But we'll say that the minimum here is 4. Q1 is going to be the bottom of our box. So if we follow this over, let's call that 10. It looks about halfway between 0 and 20, so we'll call that 10. The median is the line in the middle of the box. Let's call it 16. I don't know. We're just rough estimate here. So we have 4, 10, 16. Q3 is the top of the box. Let's call it 27. Sure. So 4, 10, 16, 27. And then the maximum. Try to guess what the maximum is. You don't even have to pause the video. I'll give you a couple seconds. I'm going to take another sip out of my pop. I will tell you that the maximum is not 50. So a lot of students guessed 50 because this is the end of the whisker. I will also tell you it is not 401. So a lot of students guess that it's 401 because this value is up here. The maximum is right around 80 pairs of shoes. You see all of these little dots here. You might be able to guess what these are, but these are outliers. Outliers can still contribute towards the minimum and the maximum, So the maximum, even though the whisker ends down here, the maximum is way up here, and the maximum is 80. So our 5-number summary, what you should be writing over here, is 4, 10, 16, I think it said 27, and then 80, or if you have numbers somewhere around there. A common question that I get then is, well, what does that 401 mean? Well, what it means, if I go back to my data set, if I scroll down to row 401, oops, too far. So this is a female, shocking, junior that likes the color red best. If I go all the way over to shoes, this person has 80 shoes. So what that 401 indicates when we look at our graphs on SPSS, that tells us where in the data set the value is actually located. There might be times where we want to isolate outliers, or we might want to know other features about these outliers. So this just helps you point back to the data. The circle or the star, you don't need to know the difference between those two. You still follow it over, and that's still the actual value that we are interested in. What I'm about to tell you, you don't have to know, but to determine outliers, what SPSS does is they take this distance right here, which we will give a name to here shortly, but the distance from Q3 to Q1, they multiply that by 1.5. And then anything that is more than 1.5 of these distances away, they consider an outlier. So this guy right here is just past 1.5 of these away from Q3. You don't need to know that. SPSS, they just tell us what the outliers are. All right. So what can we tell about the shape of the distribution based off the box plot? So there's 4 things we can talk about: the center, the variability, the shape, and outliers. So the center, remember the center we want to find is the median, where half the data is below, half the data is above. Box plot does a very, very good job of that. It's the line inside the box. Variability. We can calculate IQR and the range. You might not know what the IQR and the range is just yet. But remember what I said earlier, variability is kind of hard to talk about. It's easier to compare 2 graphs together when talking about variability. But the IQR, that's this distance right here. The IQR stands for interquartile range. The definition is already on the next page if you want to peek ahead. But this can tell us something about the variability. It tells us, how much spread is there between the 25th percentile and the 75th percentile. So this is the middle 50% of the data. The shape. Can't really tell a ton using a box plot. The next graph that we'll talk about is a little bit more powerful when it comes to shape. But we can determine the skew. So this is obviously not symmetric. If I draw a line down the middle, and here the middle is just the median. If I draw a line down the middle, this side doesn't look anything like this side. So this is either skewed left or it is skewed right. If I go back to this graph, skewed left, the data values to the left are more spread out. Skewed right, the data values to the right are more spread out. Well, I don't have left and right, I have up and down. But if you think about throwing this down on its side, remember on a number line, the smaller data values go to the left, the larger data values go to the right. When we have a vertical box plot, the smaller data values are down, the larger data values are up. So if we can think about throwing this down on its side, so this graph is skewed upwards. It's skewed towards the higher numbers, which means it's skewed to the right. So not symmetric, this data is definitely skewed to the right. Now, a common misconception here about box plots. Students will look at this distance, and they'll say, oh, this covers a lot of distance from the maximum to Q3. That is so much wider than Q1 to the minimum, so there must be a lot of data values here because there's a larger range of values. It's actually kind of the opposite. The data values here are less dense than the data values here because remember, our 5-number summary, it breaks the data down into 25% chunks. 25% of the data is between the minimum and Q1, 25% of the data between Q1 and the median, 25% of the data between the median and Q3, and 25% of the data between Q3 and the maximum. So there's just as much data in this little range as there is in this whole range right here. So much less dense up here than it is down here. These data values are much more spread out, and this graph is skewed to the right. It's skewed towards the higher values. A couple things that we cannot determine from a box plot. We can't determine how many modes there are. So if I look at this graph, I don't know how many modes there are because it doesn't show us the distinct peaks. That's just not something that a box plot does. And the other thing along those same lines, it doesn't tell us if it follows a normal distribution either. And then finally, outliers. SPSS will detect these for us. So all of these guys are outliers. The stars, they're extreme outliers. But again, you don't need to know that. So to fully describe the shape of this box plot, you can tell me where the median is. You can tell me the IQR. I'm not really going to care about that because the IQR doesn't really tell us a ton. So this is what I do want you to tell me when describing the shape of a box plot. You need to tell me where the median is, which direction the data is skewed, or if it's symmetric, and then presence of outliers. So if I was describing the shape of this box plot, I would say that the median is around 16. It is skewed to the right with 15 or so outliers on the high end. Now, you don't have to go in here and say, there's an outlier at 80. There's an outlier at 78. There's an outlier at 72. Just say that there's outliers on the high end. So median at 16, skewed right, outliers on the high end. Oops. So I used these two terms already. The range is the maximum minus the minimum. This is a number. It is the answer to a subtraction problem. It's not, the range is not from 4 to 80. We would say that the range is 76 because it's 80 minus 4. And similarly, the interquartile range, or IQR. Again, this is an answer to a subtraction problem. It's the distance, or the difference between Q3 and Q1. So the IQR is the height of the actual box here. And the larger the IQR is, the more variability there is. The smaller it is, that means that the middle 50% of the data is really, really tightly clustered together. All right, section 3.4, descriptive statistics, histograms. Here's an example of a histogram, but before we do that, I want to explain why we need to do a histogram. So again, this is your data, and this is for Facebook friends, as you can clearly see right there. And I made a bar graph for Facebook friends. This doesn't really do a whole lot for me because pretty much everyone has their own unique number of Facebook friends that they have. Now, there is one data value where 6 people have, and I am quite confident that this number is exactly 300. I'm guessing that out of these 6 people, that at least 5 of them, or 4 of them, at least 4 or 5 of them, didn't do what I asked and didn't actually look up their Facebook friends. And they just said, I have around 300. This is why I asked you to specifically look up how many Facebook friends you have, because this helps illustrate it's difficult, or it doesn't show up a ton where 2 people just happen to have the exact same number of Facebook friends. It can happen. I mean, there's maybe 50 or so different values where there is more than one person. But remember, this is out of over 750 students. The vast majority all have their own unique number of Facebook friends. So this graph does not tell us a ton. what we can do instead is we can do a histogram. This is the exact same data as that previous graph. But instead of giving each data value its own little bar, what we do here is we say 1, 2, 3, 7. So here, everyone that has between 0 and 70 Facebook friends, you go in here. Everyone that has between 71 and 140, you go in here. Everyone between 141 and 210, you go here. So on and so forth. So instead of just saying, well, everyone that has exactly 236 Facebook friends, you go in this bar, we're going to take a range of values. And this graph, so much easier to tell stuff about the data than this graph. So a couple quick things about histograms. The size of the intervals has to be the same all the way through. So that's why I said if this was 0 to 70, this one has to be 71 to 140. This one has to be 141 to 200. I'm not so concerned that you can figure out the actual range of each interval. Not that important. But you just need to know that they all have to be the same size. So histograms, a lot better than bar graphs for quantitative data. So here we have shoes again. So this is the exact same data as we had for our box plot up above. We cannot approximate a 5-number summary from this. We can approximate the minimum and the maximum, but it's near impossible to find Q1, the median, and Q3. So that's the advantage that a box plot has. If you had the 5-number summary, you could quick make a box plot. So if you know that the minimum is 4, the median, or Q1 is 10, the median is 16, 27, and 80, you could draw a box plot over here very, very simply. Now, you wouldn't be able to come up with the outliers, but you could draw a very simple box plot. We probably won't do that at all in this class. We have SPSS. We have the tools that will make it for us automatically, so we probably won't spend a whole lot of time on that. But you can't really just draw a histogram. It would be really, really difficult without a computer program. But what can we tell about a histogram? So for the center, I did already mention it's hard to find the median. So the center, I'm going to use that term a little lightly here, we can tell where the peaks are. So here again we have unimodal data. Now I do agree there's a little dip here and 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 here. But in general, this graph goes up once and then it comes back down. So we say that it's unimodal. So the first thing that you can tell me when describing the shape of a histogram, where's the mode? Now again, you don't have to go in here, count the number of bars, and be like, all right, so this one is between 7 and 8 shoes or something like that. All you have to tell me, the mode is around 7. Perfect. So, and then if it's bimodal, do tell me where both modes are. So if we go back here, I would say that the modes are at 2 in 4 minutes and 30 seconds. Variability. We can determine if a lot of the data is clustered together or if it's more spread out. Here, a lot of the data is right here. So a lot of the data is really, really scrunched. Now, if there was another big peak over here, or if we go back to this, there's going to be, at least relatively speaking, this is going to have a wider variability because you have 2 sets of data compared to this, where a lot of it is clustered together. Again, though, variability is kind of hard to describe. So when we're describing the shape of a histogram, you don't have to include anything about variability in there. Shape. Here we can determine the skew, just like with a box plot. And just like with a box plot, this is skewed to the right. The data values to the right are more spread out. It doesn't matter if we use a box plot or if we use a histogram. If it's skewed right using a box plot, it's going to be skewed right using a histogram as well. But we can also determine the number of modes, and we can check if it's bell-shaped. So here the number of modes is 1, and it's not bell-shaped. Remember, bell shapes they're symmetric. So if you have skew, you know that it's not bell-shaped. And then outliers. This is one of the drawbacks to a histogram versus a box plot. This is going to be visual detection only. For sure, these two are outliers. That has a height of 2. These 3 bars I would probably call outliers. My general rule of thumb that I like to use, if there's 2 empty spots and then some data, call it an outlier. If or on a homework or on an exam, if I want you to call something an outlier, I'll make it very, very clear that I want you to call that an outlier. So fully describe the shape of this histogram. It's unimodal. The mode is around 7. It is skewed to the right with a few outliers on the high end. So again, it doesn't matter if we use a box plot or a histogram. The shape of the distribution, the shape of the data is the same. The only difference is what we can actually say about the data. Oh, that's pretty much exactly what we have here in my notes. The shape of the distribution does not change depending on what type of output we use. Rather, what we can tell about the shape can change. All right, section 3.5, descriptive statistics, numerical summaries of center. So the mean is a numerical summary of center. My guess is most of you have heard of the mean. And then basically the mean is the average, and because I'm a statistician and I have a math degree and stuff like that, it's the arithmetic average. So it's not the geometric mean, it's not a harmonic mean or anything like that. But the mean is the average. So it's the sum of the observations divided by the number of observations. So if I wanted to find the average height of our class, well, I could do one of 2 things. I could just ask everyone what their height is, add up all those observations, and then divide by the number of students in the class. Or I could have you guys go out to the hallway, have you all lie down on your back, put your feet on top of the person's head in front of you, measure the total distance, and then divide by the number of observations. Either way is fine. It's the sum of the observations divided by the number of observations. The deviation, this isn't so much a measure of center, but this is going to come up in the next section, in section 3.6. But a deviation is how much each data value differs from the mean. So my height is 5'9". Let's say, for nice round numbers, the average height of everyone on Grand Valley's campus on Monday or Tuesday, whenever I see you guys, is 5'8". What that means is I have a deviation of 1. My height is 1 inch greater than the average. And that concept is going to be really, really important for what we do in the future. But a deviation is just simply the difference between each data value and the mean. The median, also a measure of center, but we've already covered that, so we don't need to get the definition down here again. Remember, not talking about the mode as a measure of center, not talking about the most commonly occurring number as a measure of center, because it's not always going to be that way. So the mean and the median are 2 measures of center. Now, robust statistics, this isn't like a specific numerical summary, but rather a group of statistics, a group of numerical summaries. And what a robust statistic means is it's not heavily influenced by outliers. It's not greatly impacted if we have extreme values that greatly differ from the rest of the data. So if you think about if we had Yao Ming, if you don't know who Yao Ming is, he's a 7'5" Chinese basketball player from like 10 years ago. If he was in our class, he would be considered an outlier for height. A robust statistic, it's a numerical summary that doesn't really care exactly how tall Yao Ming is. So a couple quick examples of robust statistics. The median is a robust statistic because the median doesn't care how far out you are. It just cares if you're less than or if you're greater than itself, because it needs to make sure that 50% of the data is on both sides. Q1, Q3, and then therefore the IQR. These are robust statistics because if you're an outlier, you're not in the middle 50% of the data. So you are not affecting Q3 or Q1 or the IQR at all. So what we've seen so far, Q1, Q3, IQR, and the median are all robust statistics. They're not impacted by outliers. Some examples of non-robust statistics. The mean. If Yao-Ming was in our class, that one data value is really going to pull the mean in its direction. Or if we had a little person in our class that was like 3 foot, their one data value is really going to pull the mean down in their direction. The range, obviously not a robust statistic, because if you are an outlier, you can heavily influence the minimum or the maximum because you are on the extremes. So the minimum, the maximum, the range, and the mean are examples of non-robust statistics. Okay, I have no idea how long this video is. Let's take a peek over here. 40 minutes. Wow, that was longer than I expected. Yeah, if you made it this far, you've already watch the whole video. Make sure that you read through this section. I apologize for not being in class. I really wish I could have been there. I was sick. I will take questions on this material on Tuesday, but you're expected to kind of get through this yourself a little bit. I will be there for clarification, though. Depending on when you watch this, have a great weekend. Go green. I'll be in a lot happier mood if they win. And, yeah, I will see you guys on Tuesday.